We are going to see more flexible machine, which is the non-deterministic finite automata with null transition. So here we allow the machine to transit on behalf of the null, and this is more flexible as compared with NFA. So see, if we are going for the examples, like consider the language L 0 star 0 1 clean star and 0 clean star. If we consider this language and want to construct the DFA or finite automaton for this, then you see that we feel much difficulty. Even if you go for the NFA, then also you have to think a lot. So one way to construct the machine is like this. See, if what is the intuition of this language? You have 0 clean star, means any number of zeros, maybe null also, and 0 1 clean star, this can also be null, or 0 1 0 1 you can repeat, 0 clean star. The smallest string of this language is null. You have the smallest string which is null, and then you may have only single 0, or you may have 0 0 1, or you can have 0 0 1 0, like the things. Okay, so you can construct like this. So the smallest string of this language is null string we have. So see, one way to construct the machine like this. Say if you are going to start, say for example, we have Q0, this is the Q0, and 0 clean star means you can repeat for the 0, and any number of times you can have the 0, maybe 1 time, 2 times, or any number of times. Then if you go for the other parts like 0 1, so how can you do? If you can say you are in the state Q1, and say this is the state Q2, and if you are at Q1, then you are going to the state Q2 for the case of 0, and if you are at Q2, come back to the Q1 for the input 1. So in this case, you are going to repeat 0 1 0 1 any number of times. Now finally, for the third part, which is the 0 clean star, you can say we have the state like Q3. If you are having the state Q3, then 0 clean star. Now see how you can join actually. So this corresponds to the first part, 0 clean star. Then this is corresponds to the 0 1 0 1 clean star, and this is corresponds to the 0 clean star. So how you can join? So what is the intuition of this kind of machine is that once you finish this part, once you have read the zeros, then you can go for the 0 1 0 1 any number of times. So from Q0 you can move to the state Q1 by making the null transition. And similarly, once you finish this part, then you can go to the state Q3 for accepting the zeros for the null transitions. So this is the machine for the language 0 clean star, 0 1 clean star, and 0 star. But this is the machine, this is the different machine we have seen earlier. Here, what is the difference? The difference is that here we allow the machine to transit from one state to the other state by not consuming the input, means by null transitions only. This means at the state Q0, machine has option whether to consume the input or whether it should not consume the input. When machine is not willing to consume the input, it means it can follow the transitions which is null, and it can move to the state Q1. Once machine is at the state Q1, then machine has also choice whether it can read the input or whether it can transit the state to the Q3. And for transiting the state from Q1 to Q3, it is not required to consume the input by making, because you have the null transition. So machine can, by by following this null transition, machine can transit without consuming any input. And this is the case where you can say that machine is going to make the guess. So whenever machine is at the state Q0, it has to make, it has to think whether it should consume the input or whether it should not consume the input. Which machine has to make a choice. From the state Q1 also, since you have given the null transition here, machine has the choices whether it should read the input or whether it should not read the input. So this is the case of the non-determinism. Even you have the machine where you can explicitly mention the transitions for every input, maybe for 0 or 1, your machine may go to the unique places, but having the null transition itself, this says that this is the non-deterministic machine. So this is the different kind of machine which we say that machine is following the null transition, means machine has choice to consume the input or it should not consume the input. So how we can define formally a non-deterministic finite automaton with null transition, which we say in short NFA-Null. This is NFA-Null is a 5 tuple. Just like we have seen in case of the finite automaton DFA or NFA, the NFA-Null, a non-deterministic finite automaton with null transition, which we say in short NFA-Null. So NFA-Null is a 5 tuple M Q sigma Q0 A delta, where what is Q? Here Q is the finite set of states. The sigma, this is the finite set of input symbols. Means alphabet. Okay, alphabet. This Q0 belongs to Q. This is the initial state. A set of final states. And delta is what? Delta is the transition function. So here again we have the same thing. Q is the finite set of states. Sigma is the finite set of input symbols. Q0 is the initial state from where your NFA null starts. A is the set of final states of your NFA, and delta is the transition functions of your. Here one thing is more. In this machine, we have not designated yet the final state. So Q3 we will make as the final state here. This is the final state. And since you know that the smallest string of this language is null. So when the smallest string is null, then your initial state must be the final one. But here we don't require to make the Q0 as the final state, because once you are at the Q0, without consuming input, you can reach to the Q1, and from Q1 also, without consuming any input, you can reach to the Q3. Hence, once machine stops at the state Q0, this means it can also reach to the Q3. And in this, that's why we don't require to mark Q0 as the initial state. And the only final state in this case is Q3. So Q3 is the final states. So here we have only one final state in this case. Now everything is same, just like we have seen in the NFA, set of states, input symbol, initial state, final state, and transition function. But the way you define the transition function makes the difference. So how you can define the transition function here? The transition function delta is defined like this. You are in some state Q and you have the input symbol and union null. So here you allow the machine to transit on behalf of the null also. So that's why you have, since in the case of input symbols, the null is not included, explicitly you have to include this. And then it goes to the any subsets of Q. Okay. So your machine goes to the some subset of Q. Again, it can have, your machine can go more than one place instead of only one place. So this is the set 2 raised power Q is the set of subsets of Q. So this is same, only the difference is that from any state your machine can have null transition also. This you need to ensure. That's why this is the NFA with null transitions. So this this is the way you can say that machine is going to transit on behalf of the states and on behalf of the input symbol, and on behalf, maybe in some cases you allow the machine to transit without consuming any input, means with the help of the null transitions. So how actually machine is going to execute? So see, if you are at the state q0, so you are at the state q0, okay, and somebody gives you the input 0. So what are the places your machine can reach on this FA? So whenever you are at q0, see, and you supply the input 0 from the state q0, then you know that here is the transition, and q0, from the q0, for the case, from the case of for the input 0, you are going to make a loop, and hence your machine can be in the same state as the q0. This is one possibility. When machine is at the q0, and since you have the null transition here, without consuming any input, machine can also reach to the q1. So once machine halts at the q0, then it can also move to the q1. So machine can also be at the state, say this is the q1. Machine can go to the q1 also. It may happen that whenever you are at the q0 and your machine is required to read the input 0, then machine thinks that, okay, since I have the null transition, without reading the input, I can transit first, and machine transit to the state q1. Once machine is at the q1, it can read the input 0, and once it reads the input 0, it means it goes to the state q2 also. So machine can also be at the q2. This is, so machine can also reach to the state q2. Okay. Other possibility, machine can, without consuming the input, machine can go to the q1. Machine thinks that, okay, I should not consume the input. It can reach to the state q3 without consuming the input, and finally at the q3 it can execute. It can read the input 0, and it remains in the same place q3. So other possibility is that your machine can go to the state q3. This is the way. So you have seen that whenever you have the input 0, your machine can be at the state q0, your machine can be at the state q1, your machine can be at the state q2, or your machine can be at the state q3. So this happens because of the null transitions. So how would you know that from some state for some input where your machine can reach? Means you have to consider the null transition, means you need to determine the null closure. How you can define the null closure? The null closure of the set S we denote by writing the null S, and how we can define is defined as follows. So How you can find the elements of the null closure of S? This is first condition. Every element of the set S is an element of the null closure of S. So see how it is. Let us assume that you have the Q0 and Q0, this is the Q0 and this is the subset of Q, and null closure of Q0 we can write like this. So null closure of Q0 we denote by writing this. So how you can define null closure of Q0? So step 1 says every element of S, this is the S, every element of S is an element of null S. So you have only one element which is the Q0. So you can say Q0 is a member of the set null closure of Q0. Now you can follow the second step. So this says for every Q which is in the null S, every Q which is in null S, every element of the set delta Q null. See, this is the set. Output of this is what? Output of this delta Q null is some subset of Q. So you have some elements in this set is a, so if the every element of this set is also the element of the null S. This means like this, if you are at the Q0, see, is there some transition for the Q0 here? So you have seen that you have the transition for the Q0, means you have to consider the delta Q0 null. And you see that delta Q0 null is what? This is the Q1. You are going to the Q1. This is the set. An element of this set is Q1. So every element of this set is also the member of null closure of Q0. That means Q1 is a member of the set null closure of Q0. Now this is the, we have seen the case of Q0. Now you can go for the Q1. So you have to see that is there some transition at the state Q1 for the null. So delta Q1, if you are at the state Q1 and you have the null, and you can see that whenever you are at the state Q1 you have the null transition and your machine is going to the state what? Q3. This is the Q3. So Q3 is also an element of this. Whenever you are at Q3, see the null transition, you don't have any null transition. So since you don't have any null transition, means you are at the Q3 and you are at Q3 and you are getting the null transition, and you see that you are not having any null transition, means this is the empty set, and means these are the only elements in the null closure of the set. Okay, so this is the null closure of, this is the way you can determine the null closure of this set. So that's why only these states, only once you obtain the elements of the Q using the step 1 and 2, these are the only the null closure of the set S. So you can say no other elements of the set Q are in null closure of the set S. So you can use step 1 and 2 for obtaining the null closure of the set, means you need to determine the effect of the null transitions. Once you are at the Q0 and you have the null transitions, then you are observing that where your machine can reach without consuming any input. Means once you are at the state Q0 and even you are not going to consume the input, since you have the null transition, your machine can go to the Q1. Your machine, Once your machine is at the Q1, your machine can also go to the Q3. Means if you are if, whenever you are at the state Q0, then for the in case of the null, without using reading any input, you can be at the Q0, or you can be at the Q1, or you can be at the Q3. Now the question is that this is the effect of the null closure. When somebody asks you that when you are at the state, some state in the machine, say you are at the Q0 and you are taking the input, say 0. So whenever you are at the state Q0 and you have the input 0, where you can move. So transition says that you can move to the, for the case of Q0, if you see the transition, delta Q0, 0, the output is what? Q0 means you are in the same state. So this is the transition, but you have to see the effect of the null also. Whenever you are at this state, you can also be at this state, or you can also be at this state. And you are, once you are at the Q0, you don't require to read the input. Machine think that okay, I will not read the input, I will read later, and without consuming the input, machine may be turned into the state, and machine can be at the Q1, and when machine is at the Q1, it can read the input Q0, machine can also go to the Q2. So these are the options. So how would you know that whenever you have some input from some state where your machine can reach on effect of the null transition? So for that, actually you need to see the definition of the delta star, and this is important. So how we can define the delta star here? M is equal to Q sigma Q0 A delta be an NFA null. Then delta star function, which says that you are at any state, and if you have some string from the sigma star, if you are in some state and you are given, machine is supposed to read the input string from the sigma star from that state, what are the states your machine can go? So here again, machine can go to any subset of Q. Machine can go to the more than one place. So how you can define? Then the transition function delta star can be defined as follows. So how you can define? Just like we have seen in case of the finite automaton DFA, whenever you are in some state and you have the null string, your machine remain in the same place like Q. In case of the NFA, we have seen that whenever is your machine in some state, and from that state, if it is reading the input string null, then it goes to the same state, but you have to write in the form of this set because your machine goes to any subset of Q. In the case of the NFA null, your machine remain in the same state Q, but you have to consider the effect of the null transition. Hence, you need to find out the null closure of the set Q. So this is the trivial case. In the second, for any Q belongs to Q, Y belongs to sigma star, and some input A which is taken from the sigma, the transition function delta star Q YA is defined as follows. So YA is the bigger string you have. How you can define in case of the NFA? In case of the NFA, we have defined like this, which is equal to union transition from the state P or taking the input A, where what is the P? P belongs to the delta star Q Y. So whenever you are in the state Q, first you need to know that on reading the input string Y from the state Q, where you can go. So this is the set, and for every element of this set, you need to know that if you are in these states and you need to read the input A, where your machine can go. So for every element which is in the set delta star q y, you need to consider, from that state you need to consider for the input A and then make the union. But since this is the NFA null, you have to see, after computing this set, you also see the effect of the null transition, and hence you have to compute the null closure. So this is the way you can find out the states where your machine can reach for some string beginning with some state. This is the machine we have seen for the case of the, for the language, the L is equal to 0 clean star, then 0 1 clean star, and 0 clean star. This you are at the state q0 and you are given the string 0 where you can move. So you need to compute delta star q0 0, and we need to know that what are the state where your machine can reach. So how you can compute delta star q0 0? So you can use the definition of delta star here. So see, first you need to know that whenever you are at the q0 and you have the null string, where you can go, means you need to compute delta star. You are in the state q0, you have the string null, where you can go. So you know that you are going to the state q0 and this is the subset, and you have to consider the null closure. And definition of null closure says that every element of the set S is also an element of the null closure, means q0 is one element. From q0 you need to see the transitions of the del for the null. So you are at the state q0, you have the null transition here, and on behalf of the null transition from the state q0, you are at the state q0 and you have the null transition, your machine goes to the state q1, and hence q1 is also the element of this. Now you have to consider the q1 also. From q1 you need this, you have the null transition and your machine goes to the state q3. When you are at the q3, you have the null transition, you don't have the null transition at the state q3, means your machine goes to the empty state, and hence these are the only states in the null closure of the q0. So this is you have computed. Now you need to compute the delta star q0 0. So how you can compute this? So you can use this second step, and which says that you have to compute first p 0, where p is what? Where p belongs to q0, q1 and q3. Why q0, q1, q3? Because delta star q0 null is equal to, for once your machine is taking the input string null at the state q0, it can go to the q0, q1 and q3. Once it can be at the q0, q1 or q3, and from these state, if it takes the input 0, where your machine can go. From the q1 it takes 0, where your machine can go. From q3, once it takes 0, where your machine can go, you need to determine and then make the union, and then finally you have to compute the null closure of this set. So this can be, this is what, see, whenever you are at the state q0, input is 0. You are in the state q0, input is 0. You are in the same place q0. Whenever you are at q1 and input is 0, you are at q1, input is 0, you are going to the state q2. Okay. Whenever you are at the state q3, input is 0, you are at q3, input is 0, you are at the state q3. Are getting? So You have to consider for every p, means p can be q0. Once it is 0 and your input is 0, so you are in the state q0. If your p is q1 and you are taking the 0, input is 0, your machine goes to the q2. And p is q3 and from q3 you have 0, your machine is going to 0. And this is the, and finally you have to consider the null closure of this set. So null closure of this set is what? This says that every element of this set is also an element of null closure. q0, q2, q3, these are the elements. From q0 you have the null transition, you go to the q1. So q1 you can also add. Okay. From q2 you have the null transition, no, empty. From q3 you have the null transitions, no, empty. From q1 you have the null transition and you are going to the state q3, but q3 is already here. So these are the only state. This means whenever your machine is at the state q0 and it takes the input 0, it can go to these states q0, q2, q3 and q1. That's why we have seen earlier once you are at the state q0 and if somebody gives you the input 0, your machine can be at the q0, your machine can be at q1, q2 or q3. This is the way we have computed. And similarly, machine can read the other input and you can say 0, after 0 you can have further 0, then from, if you are at the q0 and you have the 0, you can machine goes to the 4 places q0, or machine can go to the q1, or machine can go to the q2, or your machine can go to the q3 if you have the 0 again. If machine is going to read 0, then it can again from the state q, it can go to the q0, it can go to the q1, it can go to the q2, it can go to the q3. This is the way. From the q1, if you are having the 0, from q1, if you are having the 0, machine goes to the q2. So your machine can go to the q2. Since whenever you are at the q1, without reading the input, your machine can also go to the q3, and from at the state q3, actually your machine can read 0, and hence it can also be at the q3 like this. So this is the q3. This is. Similarly, whenever you are at q2 and you have the input 0, since there is no transition for the 0 from the q2, this means empty state. It is not going to, it is going to the empty state. Whenever it is, your machine is at the q3 and your input is 0, your machine is at the q3. So this is the way on reading the input 0, 0, on reading the input 0, 0, this is the non-deterministic computation. Mystic computation. So see, for the once machine takes the input 0, 0, these are the, this is the tree. Machine can follow this path. It can, once machine follows this path, then it end up with the q0, and this is not the final state. Then machine can make the other guess. Machine can follow this path. It is going to end up with q1. This is not the final state. Machine has other choice. It can go to the q2 also, but this is also not a final state. Then machine has further choice, and machine can go to the state q3, and q3 is the final state. This means this is in the language. So this is the way machine is going to make the guess, and if at least one such guess is there for which machine is able to reach the final state, then you can say that the input is in the language. Okay. So this is the situation you have. Now you can see the transition table for this machine. This is the NFA-Null for the language. You can construct the transition table for this NFA-Null. So you can say here This is the Q. Now you have the three situation. One is null transition. You have to consider the null transitions. Other is the input either 0 or 1. So if you are at the state Q, and you can have the null transition where your machine can go. You can see if you are at the state Q and if you have the input 0, where your machine can go. If you are at the state Q and your input is 1, where your machine can go. So this is you need to determine. So Q can be Q0. So if you are at the state Q0 and you have the null transition, where your machine goes, it goes to the state, this is the Q1. So whenever you are at Q0, you have the null transition, you are going to the state Q1. Whenever you are at Q0 and your input is 0, you are in the state Q0. Whenever you are at the Q0 and input is 1, where you are going? From the Q0 input is 1, we don't have the transition. It means you go to the empty state here. This is one. Now see, if you are at the state Q1, so if you are at the state Q1 and you have the null transition, yes, you have the null transition, and you are going to the state Q3. Okay, whenever you are at Q1, you have null transition, you are going to the Q3. Whenever you are at Q1, your input is 0, so you are going to the state Q2. You are going to the state Q2 for the case of 0. If you are at Q1 and input is 1, there you go. You are not going anywhere, means this is empty. Now you can go consider the state Q2. Whenever you are at the state Q2 and you have the null transition, no. So you don't have the null transition, means empty. Whenever you are at the state Q2 and you have the null transition for 0, your input is 0, you are going to empty state. Whenever you are at the Q2 and you are reading the input 1, so whenever you are at Q2 and input is 1, you are going to the state Q1. This is the way. Okay. So whenever you are at Q2 and input is, you don't have the null transition at the Q2, hence this is the empty state. Whenever you are at Q2 and input is 0, you don't have the transition for 0, hence you are going to the empty state. You are at Q2 and input is 1, you are coming to the Q1. Now you are at the Q3. This is, you are at the Q3. So whenever you are at Q3, whenever you are at the Q3, you see you don't have the null transition, so you are at the Q3 and del Q3 null is empty. You are at Q3 and input is 0, you are going to the Q3 itself. So this is the Q3. Okay, if you are at Q3 and input is 1, this is the empty state. So this is the transition table of NFA-Null table. This is the way you can, just like in other cases, you have the transition table of the NFA-Null. Okay. Now see the situation, and if you are at the state Q0, instead of the input, like either you have the null transition or 0 or 1, instead of this, if you are at the state Q0 and you think you want to know that if somebody gives you the strings 0, you have the string 0 which is taken from the sigma star, then for the string 0, where you can reach, so you can consider the delta star transition here, and delta star, you are at the state Q and you for the input 0. Similarly, you can find out the transition for the delta star, you are at Q and input is 1. So how you can determine? So delta star Q0, once you are at the state Q0 and your input is 0, input string is 0, where your machine can reach? You can see we have computed earlier and we have seen that if you are at the state Q0, your input string is 0, you are going to the state Q0, Q2, Q3, Q1, means you are going to the every state Q0, Q1, Q2 and Q3. So you can just write here, whenever you are at the Q0 and input string is 0, then you can go to, your machine can go to the Q0, your machine can be at the Q1, your machine can be at the Q2 and your machine can be at the Q3. So this is the possibility. Whenever you are at the state Q0, your input is string is 1, means whenever you are at the state Q0 and input is 1, you need to compute it. So how you can compute it? You are at the state Q0, input is 1. So you are at the state Q0 and you have the null string, then you know that the null closure of Q0, and null closure of Q0 is what? Null closure of Q0 we have computed, and null closure of Q0, Q0, Q1 and Q3. And once you are at the Q0, whenever you are at Q0 and your input is 1, where you are going? Whenever you are at Q0, input is 1, you are going to the empty state. Whenever you are at Q1 and input string is 1, where you are going? You are going to the empty state. Whenever you are at Q3, input is 1, where you are going? Empty state. Okay, means this is empty and null closure of empty state is again empty. So hence you can say this is the empty and your machine goes to the empty state. Okay. Now, okay, whenever you are at Q1, and you are taking the input 0. So you are at Q1 and your input is 0. So you are at Q1 and input is 0. So first you need to compute the null closure of Q1, and null closure of Q1, you know that null closure of Q1 is what? Null closure of Q1 is the state Q1, you have the Q1, okay, and from the Q1 you have the null transition, so you are going to the Q3. So this is the null closure of Q1. So whenever you are at the state Q1, you have the null string, where you can go? You can go to the Q1 or you can be at the Q3. So this is the null closure of Q1. And from these state, if you have the input 0, then if you are at Q1 and input is 0, you are going to the state Q2. Whenever you are at Q1, input is 0, your machine goes to the Q2. Whenever you are at Q3, input is 0, your machine goes to the state Q3. And next, you have to consider the null closure. Null closure of Q2 is what? Null closure of Q2, Q3. So you have the Q2 and Q3. From Q2, you don't have the transition for the null, so empty. From Q3 also, you don't have the transition for the null string, so you have Q2 and Q3. Q2 and Q3. So this is the Q2 and Q3. Okay. For the case of 1, instead of 0, if you have the 1 here, then if you are at Q1 and having null 1, empty state. If you are at Q3, So input is 1, empty state. So null closure of empty is empty. So again, this is what? Empty. Now, whenever you are at Q2 and you have the input string 0, so whenever you are at Q2 and if you have the null string, then you are in the null closure of Q2, and null closure of Q2 is what? Only the Q2. So from Q2, if you are getting 0, where you go? You are going to empty state, and null closure of empty is also empty, and hence this is empty. Now, whenever you are at Q2 and input is 1, so null closure of Q2 is Q2. From Q2, your input is 1, you are going to the Q1, okay? And null closure of Q1 is what? You have null closure of Q1 is Q1, and from Q1 you have the null transition, you are going to the Q3, and from Q3 null transition empty. So this is the case of, for the case of 1. Now you are at Q3 and input is null 0. In string, input string is 0. When you are at Q3, input string is 0. This means the null closure of Q3 is remains Q3. From Q3 you are getting the 0. You remain in the 0. Null closure of Q3 is again Q3. So you are having the state Q3. Whenever you are at Q3, input is 1. So whenever you are at Q3 and input string is 1, so null closure of Q3 is Q3. From Q3 you are getting 1. There is no transition, means your machine goes to the empty state. Null closure of empty state is empty, and this is the case. So this is the way you have obtained the situations. So this is the case when your machine takes the input string from the state Q0, Q1, Q2 and Q3, and we have seen that for the simplest string 0 or 1, where your machine can go. So this is the way you can determine the states where your machine can reach on behalf of the input strings 0 or 1 from the state Q0, Q1, Q2 and Q3. Now see, this is the NFA, and for the NFA, you cannot directly implement the NFA until you are going to convert this machine as the deterministic one. Fortunately, you have the procedure. We can convert this NFA to the DFA, but instead of directly converting this NFA null to the DFA, first you need to convert this NFA null to the NFA. Then we have seen the algorithms how we can convert the NFA to the DFA. So how we can convert the machine NFA null to the NFA? So in case of the NFA null, say you have the set of states Q, and we assume that the set of states in the NFA is Q1, and we need to decide what should be the Q1. So see, when we are going to convert the NFA null to the NFA, then we don't require additional states. Q1 is same as Q. So the same number of states behave in the NFA, and you know that sigma is the input alphabet, which is the same in the both the cases. Q0 is the initial state of the NFA null, and here also Q0 is the initial state in the NFA also. Here we have the accepting states, or you have the transitions in the NFA null. So you have some transition, you know that if you have some transitions and you are at the state Q in the NFA null, for the input 0 you are going to somewhere else. For giving the transitions of NFA, actually in case of the NFA we need to eliminate the null transitions. So how you can eliminate the null transitions? if you know that if you are in you are in some state, whenever you are in some state, okay, so whenever you are in some state like q0, and you want to know that if you are at the state q0 and you have the input 0, where your NFA can go, so how would you know? So for determining this thing, you need to compute the delta star function for the NFA null. So delta star q0 you need to consider. So once you are going to consider delta star and 0, assuming that this is the string, then you come to know that if you are at the q0, for the case of 0, you are going to the q0, q1, q2 and q3, and hence you come to know that in case of the NFA, since you are going to eliminate the null transitions, you come to know that from q0 where you can move. So for the input 0, your machine can be at the q0. For the case of q0, your machine can go to the q1, your machine can also go to the q2, your machine can also go to the q3. So NFA, transition of the NFA is the, so you can say if you want to determine where you can go in case of the NFA, so you need to determine the delta star. You have to compute the delta star of the NFA null whenever you are at the q and you have the string 0. So delta star q0 from the state q, where you can go, once you compute this function, then you will come to know. So that's why exactly this we have done actually here, and this is, you can say that these are the transitions of your, this is the transitions of your NFA. This is the NFA transitions. Okay, NFA is going to make the transitions like this. Now finally you need to decide the accepting state. So accepting state, in case of the NFA null, we have assumed that A is the accepting state, and here if you assume A1 as the accepting state, so which one will be the final state? So all states which are the final states in the NFA null are also the final states of your, so which one is the final state of NFA null? This is the final state actually. Okay, so we have, this is the actually final states here, and here you have the final state. Okay, so q3 is the final state of your NFA null, and hence q3 will also be the final state of NFA. Except this, actually you need to determine, since in the case of the NFA we don't have the null transitions, and hence when you see that the smallest string of the language is null string, and this means that initial state must also be the final state. So you need to determine how you would know that initial state should also be the final state. Whenever you make the null transitions, null closure, once you compute the null closure of the initial state, and the null closure of the initial state contains the element of the final state, then means there is a way to reach the final state from the initial state without consuming any input, and hence initial state should also become the final state. That's why you can define the A1 in case of the NFA like this. Whenever you are at the A1 is defined like this. A1 is equal to A, okay. So A1 is A union, you have to include the state, initial state Q0, when if null closure of initial state null closure of initial state intersection with the final state of A. The null closure of initial state, and once you make the intersection with the final states of the NFA null, and if this is not equal to empty. When this is not equal to empty, it means there is a way to reach the final state from the initial state, and hence this must initial state will also be the final state in the NFA. Otherwise, you just have the same final states as the NFA null. This is the case of otherwise. So this means when you say that null closure of the initial state and intersection with A is not empty, means there is a way to reach the final state without consuming any input, and hence in case of NFA, initial state should also be the final state. And if no way to reach the final state from the initial state without consuming the input, then you have the only final state which is the same as the NFA null. So this is we have converted the NFA null to the NFA. And finally you can draw the diagram. You can have the NFA. So you are having the state, this is the Q0, you have the Q0, okay, you have Q1, the same number of states we have, and you have the Q3, okay, and Q3 is what? Q3 is the final state we have determined. This Q3 is the final state, and Q0 is also the final state because null closure of Q0 contains the Q3, and this is the initial state in the NFA. Now say Q2 is also the state, so you have the Q2. This is the Q2. So we have Q2. Now you have to make the transitions. So whenever you are at Q0 and you have the input 0. So you are going to the Q0, Q1, Q2, and Q3. So from Q0 you can be the Q0, means this is the kind of loop. You remain in the Q0, or you can go to the Q1. So you can go to the Q1. This is for the 0. You can also go to the Q2. So you can go to the Q2, 0. You can, from Q0, you can also go to the Q3. So here from the Q0, you are going to the Q3 for the case of 0. See the situation. Whenever you are at the Q0 and input is 1, so here we have the empty, means you don't require to show the transition for the 1 from the state Q0. From the Q2, if you are at Q2, or if you are at the state Q1, and whenever you have the 0, if you are at Q1 and your input is 0, you are going to the Q2, Q3. So you are going to the Q2. From Q1 you are going to the Q2, and you are also going to the Q3. So this is the Q3. Now if you are at the Q2, Q1 and input is 1. So from Q1 input is 1, where you go? Empty state. You don't require to show the transition. Whenever you are at Q2, you have the input 0, you are going to the empty state, don't have the transition. But whenever you are at Q2 and you have the 1, input is 1, then you come to the Q1. So you are coming to the Q1 for the case of 1, and also you are going to the Q3. So you are going to the Q3 also. So from Q2 you are going to the Q3. This is okay. Whenever you are at Q3, your input is 0. Then for the case of 0, you are in the Q3, and for the case of 1, this is the empty. So this is the NFA you have obtained, which is accepting the same language accepted by the NFA null. So this FA is going to accept the language 0 clean star, 0 1 clean star, and you have 0 clean star. So this is the way. In this way, you can say that you have converted the NFA null to the NFA. So this is the way you can convert the machine. So we have obtained the NFA from the NFA null. So you have converted NFA null to the NFA. And once you have the NFA, then you can also convert this NFA to the DFA. So this is the way you can convert. Means for every NFA, we have seen that every NFA can be converted to the DFA. Okay, we have seen, and every NFA null we can convert to the NFA. This means every NFA null corresponds to the every NFA null, we have the equivalent DFA. Once we say this equivalent means the machine is accepting the same language as the NFA null. This means whenever you have the NFA null accepting some language, you will have some DFA that is also accepting the same language. But how you can obtain the DFA? First you need to convert from NFA null to the NFA, then you can use the algorithm to convert from NFA to DFA. So this is the way you have converted, and power of these machines, power of NFA null, power of NFA and power of DFA remain same. Only the only advantage of NFA null is construction. This is very easy to construct as compared with the NFA, and NFA is easy to construct as compared with the DFA. So if you are not able to construct DFA, then you may go for the NFA null, then you can convert from NFA null to NFA, then you can go for the DFA. Power of all such machines are same, means if you have the NFA null accepting some language, then you will also have the NFA that also accept the same language. Moreover, you also have the DFA accepting the same language, and hence power of all machines NFA null, NFA and DFA are remains same. So all machines have same power, but only the advantage is in the construction. So you can construct NFA null very easily as compared with the NFA and as compared with the DFA.